Hello, today's topic of discussion is Laguerre's polynomial. In this chapter, we have two modules. Edward Laguerre was the person who first introduced this Laguerre polynomial. Laguerre polynomials are the solution of Laguerre's equation. Laguerre's polynomial are also used to calculate numerically in Gaussian quadrature. They also have a wide range of application in quantum mechanics. So, let us learn about Laguerre polynomials. Laguerre's polynomial. Edmund Laguerre, who was born in 1834 and died in 1886, was the person who first introduced Laguerre polynomials, and which are the solution of the Laguerre's equation x d2y dx square plus 1 minus x dy dx plus n y equal to 0, where n is a positive integer. Laguerre's polynomial are used to numerically compute integrals of the form integration 0 to infinity f(x) e to the power minus x dx in Gaussian quadrature. In quantum mechanics, they are seen in the radical part of the solution of Schrödinger's equation for a 1 electron atom. They are also used to describe the static Wigner functions of oscillator systems in quantum mechanics in phase space. Let us now consider Laguerre's equation and to find its solution. We will see the solution of the Laguerre's equation are Laguerre's functions. So, Laguerre's equation of order n is defined as x d2y dx square plus 1 minus x dy dx plus n into y equal to 0, where n is a positive integer. We now use Frobenius method to solve the Laguerre's equation. So, we consider the solution of the form y equal to summation m equal to 0 to infinity C m x to the power k plus m, where C 0 not equal to 0. So, we consider this as a series solution of the Laguerre equation given by 1. We differentiate equation 2 twice to calculate dy dx and d2y dx square, and if you do that, you will be getting dy dx equal to k plus m C m x to the power k plus m minus 1 and d2y dx square as summation m equal to 0 to infinity k plus m minus 1 C m x to the power k plus m minus 2. We substitute these two values in equation 1 and we will get x times summation m equal to 0 to infinity C m k plus m minus 1 x to the power k plus m minus 2 plus 1 minus x summation m equal to 0 to infinity C m k plus m x to the power k plus m minus 1 plus n times summation m equal to 0 to infinity C m x to the power k plus m equal to 0, given by equation number 3. After simplification, we will get summation m equal to 0 to infinity C m k plus m whole square x to the power k plus m minus 1 minus summation m equal to 0 to infinity C m k plus m minus n x to the power k plus m equal to 0, given by equation number 4. Next, we obtain the indicial equation from equation 4, which is obtained by equating to 0 the smallest power of x from expression 4, and in this case it is x to the power k minus 1. And you get this smallest power by putting m equal to 0 in this expression and in this expression. And if you do that, the first one is going to give you C0 k plus 0 whole square x to the power k minus 1, and the second one is going to give you something multiplied by x to the power k. And hence, when we equate to 0 the smallest power of x in 4, we will get C0 into k square equal to 0, which will mean k have 0 as a repeated root. We now equate the coefficient of x to the power k plus m minus 1 to 0 in equation 4, and we will get Cm k plus m whole square minus Cm minus 1 k plus m minus 1 minus n equal to 0, which after simplification gives Cm equal to k plus m minus 1 minus n divided by k plus m whole square Cm minus 1, given by equation number 5. Now, in this case, the two linearly independent solutions will be given by the value of y at the point k equal to 0 and del y del k at the point k equal to 0. But del y del k at the point k equal to 0 is equal to summation m equal to 0 to infinity Cm x to the power k plus m log of x, and this log x is undefined at the point x equal to 0. So, first we consider the solution y at the point k equal to 0, which will imply y equal to summation m equal to 0 to infinity Cm x to the power m, where Cm is equal to m minus 1 minus n divided by n square Cm minus 1, which is calculated from equation 5 by putting k equal to 0, and this we named as equation number 7. Next, we substitute m equal to 1, 2, 3 dot 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 in equation number 7, and we will get C1 is equal to minus n divided by 1 square C0, C2 is equal to 1 minus n by 2 square C1, which is equal to minus of n minus 1 by 2 square multiplied by minus 1 into n C0, and this minus 1 into n C0 is obtained by substituting the value of C1 from the previous equation, and which can be simplified and put in the form minus 1 whole square n into n minus 1 divided by 2 factorial square into C0. In the similar manner, we can show C3 is equal to minus 1 cube n into n minus 1 into n minus 2 divided by 3 factorial square into C0, and hence the rth term is given by Cr is equal to minus 1 whole to the power r n into n minus 1 dot dot n minus r plus 1 divided by r factorial square into C0 for all r less or equal to n, and for r greater than n we will get Cn plus 1, Cn plus 2, Cn plus 3 and all the values equal to 0. And hence equation number 6 reduces to y equal to C0 summation r equal to 0 to infinity minus 1 whole to the power r n into n minus 1 dot dot n minus r plus 1 divided by r factorial whole square x to the power r, and this is equal to C0 summation r equal to 0 to n minus 1 whole to the power r n into n minus 1 dot dot n minus r plus 1 into n minus r minus 1 dot 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 3 to 1 divided by n minus r into n minus r minus 1 dot 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 3 to 1 into factorial r whole square. So, what you have done in the step given by equation 9 is you multiply both numerator and denominator of equation 8 by n minus r factorial. And if you do that, you will get equation number 10 given by C0 summation r equal to 0 to n minus 1 whole to the power r into n factorial divided by n minus r factorial into r factorial square into x to the power r. Now, taking C0 equal to 1, the solution of the Laguerre's equation is defined as the Laguerre's polynomial of order n and is denoted by ln x, which is equal to summation r equal to 0 to n minus 1 whole to the power r n factorial divided by n minus r factorial square x to the power r. Alternatively, one may take C0 is equal to n factorial and obtain another definition of Laguerre polynomial as ln x is equal to summation r equal to 0 to n minus 1 whole to the power r n factorial square divided by n minus r factorial square x to the power r. However, throughout our discussion, we will take the definition of the Laguerre's polynomial given by equation number 11, where we have taken C0 is equal to 1. Let us now calculate few Laguerre's polynomials. The Laguerre polynomial of order n, as seen in the previous slide, is given by ln x is equal to summation r equal to 0 to n minus 1 whole to the power r into n factorial divided by n minus r factorial into r factorial square x to the power r, given by equation 13. To calculate the first Laguerre polynomial, we put n equal to 0 in equation 13 and it will get L0x is equal to summation r goes from 0 to 0 because as n is equal to 0, so minus 1 whole to the power 0, 0 factorial divided by 0 minus 0 factorial into 0 factorial square into x to the power 0, and if you calculate this value is equal to 1. So, all you have to do is put the value of r equal to 0 and n equal to 0 in equation number 13, and since we know 0 factorial is equal to 1 and x to the power 0 is equal to 1, the expression is equal to 1. To calculate the next one, we put n equal to 1 in equation 13, and if you do that, you will get summation r equal to 0 to 1 minus 1 whole to the power r into n factorial divided by n minus r factorial into r factorial square x to the power r, given by equation 15. And if you expand this, you will get this is equal to, for r equal to 0, minus 1 whole to the power 0 1 factorial divided by 1 minus 0 factorial into 0 factorial square into x to the power 0, plus for r equal to 1, it is minus 1 whole to the power 1 into 1 factorial divided by 1 minus 1 factorial into 1 factorial square into x to the power 1. And if you simplify this, this is going to give you 1 minus x. So, L0x is 1 and L1x is 1 minus x. To calculate the Laguerre polynomial for n equal to 2, we substitute n equal to 2 in the expression 16, and if you do that, you will get equation 17 given by summation r equal to 0 to 2 minus 1 whole to the power r into n factorial divided by n minus r factorial square into x to the power r. If you expand this, you will be getting minus 1 whole to the power 0 into 2 factorial divided by 2 minus 0 factorial square x to the power 0 for r equal to 0, and for r equal to 1, you will get minus 1 whole to the power 1 into 2 factorial divided by 2 minus 1 factorial into 1 factorial square into x to the power 1, plus for r equal to 2, minus 1 square 2 factorial divided by 2 minus 2 factorial into 2 factorial square into x square. And if you add all the three terms and simplify, we will get equation 18, which gives that L2x is equal to 1 by 2 factorial 2 minus 4x plus x square. For n equal to 3, we substitute n equal to 3 in equation 19. And if you do that, you will get L3x is equal to summation r equal to 0 to 3 minus 1 whole to the power r into n factorial divided by n minus r factorial into r factorial square x to the power r. If you expand this, you will get the next 4 terms given by minus 1 whole to the power 0 into 3 factorial divided by 3 minus 0 factorial into 0 factorial square x to the power 0 plus minus 1 whole to the power 1 into 3 factorial divided by 3 minus 1 factorial into 1 factorial square x to the power 1 plus minus 1 square into 3 factorial divided by 3 minus 2 factorial into 2 factorial square x square plus minus 1 whole to the power cube 3 factorial divided by 3 minus 3 factorial into 3 factorial square x cube. If you add all these 4 terms and simplify, you will get L3x is equal to 1 by 3 factorial 6 minus 18x plus 9x square minus x cube, given by equation 21. Let us now calculate an alternative expression for the Laguerre's polynomial. So, we have to show that the Laguerre's polynomial ln x is given by e to the power x divided by n factorial nth derivative of x to the power n e to the power minus x. To prove this, we will use Leibniz theorem, which says that the nth derivative of the product of two functions u and v is given by dnu into v, where dnu means the nth derivative of the function u plus nc1 dn minus 1 u into d of v, which means the n minus 1th derivative of the function u and the first derivative of the function v. And as we continue, the rth derivative is given by ncr dn minus r of u and dr of v, which means that the n minus rth derivative of the function u and the rth derivative of the function v, and the last term as u dn v. If we write this in summation notation, this will give dn of u v, that is the nth derivative of the product of two functions u and v, is equal to summation r equal to 0 to n ncr d n minus r u dr v. Therefore, if we take the right hand side of the given expression, we will get e to the power x divided by n factorial, the nth derivative of the product of two functions x to the power n and e to the power x. Using Leibniz theorem on these two functions, we will get this is equal to e to the power x by n factorial summation r equal to 0 to n ncr dn minus r x to the power n dr e to the power x, which means the n minus rth derivative of the function x to the power n and the rth derivative of e to the power minus x. Now, we will be using the formula that the nth derivative of x to the power m, where m should be greater than n, is equal to m factorial divided by m minus n factorial x to the power m minus n, and the nth derivative of e to the power minus e to the power ax is equal to a to the power n e to the power ax. If you substitute that, you will be getting e to the power x divided by n factorial summation r equal to 0 to n ncr into n factorial divided by n minus r factorial x to the power n minus r multiplied by minus 1 whole to the power r e to the power minus x, which after simplification gives summation r equal to 0 to n e to the power x by n factorial multiplied by n factorial divided by r factorial n minus r factorial into n factorial by r factorial x to the power r minus 1 whole to the power r e to the power minus x, which on simplification gives summation r equal to 0 to n minus 1 whole to the power r into n factorial divided by r factorial square n minus r factorial x to the power r, and this expression is nothing but the expression for the laguerre polynomial by definition. We now generate few laguerre's polynomial with the help of the formula ln x is equal to e to the power x, the nth derivative of x to the power n e to the power minus x. If we put n equal to 0, we will get L0x is equal to e to the power x by 0 factorial x to the power 0 e to the power minus x, which is equal to 1. For L1x, we will get this is equal to e to the power x by 1 factorial ddx of x into e to the power minus x. And if we find the first derivative of x into e to the power minus x and simplify, we will get this is equal to 1 minus x. In the similar manner, we can calculate L2x and L3x, and we will get L2x is equal to 1 by 2 factorial 2 minus 4x plus x square, and L3x is equal to 1 by 3 factorial into 6 minus 18x plus 9x square minus x cube, and you will see these values are same as calculated from the definition. Let us consider an example where you have to express the polynomial x cube plus x square minus 3x plus 2 in a series of laguerre's polynomial. Now, from the results we have L0x is equal to 1, L1x is equal to 1 minus x, L2x is equal to 2 minus 4x plus x square divided by 2, and L3x is 6 minus 18x plus 9x square minus x cube divided by 6. So, what we have to do is we have to find x, x square and x cube in terms of the laguerre polynomial. So, from the first expression L0x is 1, from the second one L1x is equal to 1 minus x, and so we calculate x is equal to 1 minus L1x. Similarly, x square, from the third expression we will get this is equal to 4x minus 2 plus 2 L2x, and we substitute the value of 4x, and we will be getting after simplification x square is equal to 2 minus 4 L1x plus 2 L2x. In the similar manner, we will get x cube equal to 6 minus 18 L1x plus 18 L2x minus 6 L3x. We substitute all these values in the given expression of the polynomial, and we will get x cube plus x square minus 3x plus 2, which after simplification gives 7 minus 19 L1x plus 20 L2x minus 6 L3x. We have started with Laguerre's equation, and we have shown that its solution is Laguerre's polynomial. We have also obtained an alternative expression for Laguerre's polynomial. We will now see the generating functions of the Laguerre's polynomial along with some examples. We will now look into the generating function for Laguerre's polynomial. We have to show that e to the power minus xt divided by 1 minus t whole divided by 1 minus t is the generating function for Laguerre's polynomial. We consider the expression exponential minus xt divided by 1 minus t divided by 1 minus t, which is equal to 1 by 1 minus t summation r equal to 0 to infinity minus xt divided by 1 minus t whole to the power r into 1 by r factorial. And this we get by the expansion of e to the power x. So, please recall the expansion of e to the power x in the expansion of this particular term, where your x is replaced by minus xt divided by 1 minus t, and you will get equation 22. If you simplify this, this is equal to summation r equal to 0 to infinity minus 1 whole to the power r divided by r factorial x to the power r t to the power r 1 minus t to the power minus r plus 1, which is equal to summation r equal to 0 to infinity minus 1 whole to the power r divided by r factorial into x to the power r t to the power r summation s equal to 0 to infinity r plus s factorial divided by r factorial s factorial t to the power s, given by equation 24. Hence, exponential minus xt divided by 1 minus t whole divided by 1 minus t is equal to summation r equal to 0 to infinity summation s equal to 0 to infinity minus 1 whole to the power r plus s factorial divided by r factorial square into s factorial into x to the power r t to the power r plus s. We put r plus s is equal to n, so that s is equal to n minus r, where r is fixed. Then the coefficient of t to the power n is given by minus 1 whole to the power r into n factorial divided by r factorial square into n minus r factorial into x to the power r. Since s is greater or equal to 0, this implies r is less or equal to n, giving all possible values of r. Hence, all the coefficient of t to the power n is given by summation r equal to 0 to n minus 1 whole to the power r into n factorial divided by r factorial square into n minus r factorial into x to the power r, which by definition is Laguerre's polynomial ln x of order n. In this example, we have to show that integration 0 to infinity e to the power minus st ln t dt is equal to 1 by s into 1 minus 1 by s whole to the power n. Now, we take the left hand side, that is integration 0 to infinity e to the power minus st ln t dt is equal to integration 0 to infinity e to the power minus st summation r equal to 0 to n minus 1 whole to the power r into n factorial into t to the power r divided by n minus r factorial into r factorial square dt, and this we obtain by substituting the value of ln t from the definition. And if you simplify, we will get this is equal to summation r equal to 0 to n minus 1 whole to the power r into n factorial divided by n minus r factorial into r factorial square integration 0 to infinity e to the power minus st t to the power r plus 1 minus 1 dt. And if you integrate this, you will be getting this is equal to summation r equal to 0 to n minus 1 whole to the power r into n factorial divided by n minus r factorial into r factorial square gamma function r plus 1 divided by s to the power r plus 1. Now, gamma r plus 1 is equal to r factorial, and hence we will get the expression is equal to 1 by s summation r equal to 0 to infinity minus 1 whole to the power r into n factorial into n minus r factorial into r factorial into 1 by s whole to the power r, which after simplification gives 1 by s summation r equal to 0 to n ncr minus 1 by s whole to the power r, and which is a binomial expansion of 1 minus 1 by s whole to the power n, and hence we get our required result. In example 3, we have to show ln dash 0 is equal to minus n, and in the second part ln double dash 0 is equal to n into n minus 1 divided by 2. Now, since ln x is a solution of the Laguerre's equation, it is going to satisfy the equation, and we will be getting x ln double dash x plus 1 minus x into ln dash x plus n ln x is equal to 0. Now, we put x equal to 0 and ln 0 is equal to 1 in this equation, and we will be getting 0 plus 1 minus 0 into ln dash 0 plus n equal to 0, which gives ln dash 0 is equal to minus n, which proves the first part of this problem. In the second part of the problem, we take the generating function of the Laguerre's polynomial, which is given by 1 by 1 minus t e to the power minus tx divided by 1 minus t, which is equal to summation n equal to 0 to infinity t to the power n ln x. We differentiate this expression twice with respect to x, and we get 1 by 1 minus t e to the power minus tx into 1 minus t multiplied by minus t by 1 minus t whole square is equal to summation n equal to 0 to infinity ln double dash x into t to the power n. We put x equal to 0 to get summation n equal to 0 to infinity L double dash 0 t to the power n equal to t square into 1 minus t to the power minus 3. Our next step is to equate the coefficient of t to the power n from both sides, for which we have to calculate coefficient of t to the power n in the expansion of t square into 1 minus t to the power minus 3, and this is given by minus 3 into minus 3 minus 1 dot 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 minus 3 minus of n minus 2 plus 1 divided by n minus 2 factorial into minus 1 whole to the power n minus 2. And if you simplify this, you will be getting this is equal to n factorial divided by 2 into n minus 2 factorial, which is equal to n into n minus 1 by 2. And hence, we conclude that ln double dash 0 is equal to n into n minus 1 divided by 2, which completes the proof of this particular problem. We have started this module with Laguerre's equation, and we have shown that Laguerre's polynomial is the solution of the Laguerre's equation. We have also obtained an alternative expression for Laguerre's polynomial. Also, we have a generating function for Laguerre's polynomial. In our next module, which is module 2, we will look into the recurrence relation of the Laguerre's polynomial. Thank you.